Okay, so this will be the last session corresponding to chapter 6. First of all, I wanted to to repeat the proof of the Karpelevich-Mostov theorem uh, briefly, mainly because there was this commutative argument that we didn't really clarify in last session. So I think the safest bet for us is to simply repeat the proof quickly to and see how this commuted so that how this commuting argument works. So let's briefly recall the setting of the theorem. So, under the hypothesis of the theorem, we have a real semi-simple Lie algebra G0 endowed with a certain Cartan involution theta. And we also suppose that we have a homomorphism of real semi-simple Lie algebras from G0 to another real semi-simple Lie algebra H0. Then the Karpelevich-Mostov theorem states that there is a Cartan decomposition of H0 that is compatible with the Cartan decomposition of G0. Then there is Cartan decomposition of H0 compatible with the Cartan decomposition of G0. Okay. So if you remember from last time, the proof goes as follows. The first thing that we want to do is to turn this situation into into a situation that involves complex semi-simple algebras. So we complexify everything that we have in the setting. So we take G to be the complexification of G0, H to be the complexification of H0, and now G0 and H0 are real forms, so they have associated real structures. Say that G0 is associated with the involution sigma, and H0 is associated with the involution sigma prime. And obviously, we can take the complexification of F, which we will still denote by F, and from and from this we can already see that since F carries G0 to H0, we have that sigma must extend to sigma prime under F. Okay. Now recall that since theta is a Cartan involution, we can also take the complexification of theta, which is going to be an involutive automorphism of G. And the fact that that theta is a Cartan involution meant that theta commutes with sigma, and the composition of sigma with theta is going to be a compact real structure defined on G0. So we have that theta sigma is equal to sigma theta. So call this morphism tau, and this is going to be a compact real structure of G. Okay. So now we can take this compact real structure in G, and we can consider an extension of tau to H. So we have that tau is going to extend tau prime for a certain tau prime. Okay, and remember that, well, since sigma and theta commute, sigma and tau also commute, but it may not be the case that the extension of sigma, which is sigma prime, and the extension of tau, which is tau prime, commute. But we already know that we can take a conjugate of sigma prime so that it does commute with tau prime, sorry. And that was the content of the theorem previous to this, to the Karpelowicz-Mostov theorem, which allowed us to extend involutions. So from a previous theorem, we know that theta is going to extend to a certain theta prime, where theta prime is an involution corresponding to H0. And we could even be more specific by going through the proof of this result and claim that theta prime is of the form beta sigma prime beta minus 1 tau, where beta is an inner automorphism of H that extends the identity. Now, the fact that theta prime is an involution also means that, so here it should say tau prime, it means that beta sigma prime beta minus 1 commutes with tau prime. Okay? And this is going to be the key fact that we need in order to find the Cartan involution of H0. We have beta sigma prime beta minus 1 tau prime is equal to tau prime beta sigma prime beta minus 1. Okay? Now, the problem is that theta prime may not restrict to H0 because it may not commute with sigma prime. But we can construct from theta prime a new involution, which is also associated to H0, and it's the following. So take theta 1 prime to be equal to theta minus 1 theta prime theta. Okay. This is still an involution. It's associated to H0. And if we're able to prove that theta prime restricts to, that theta 1 prime restricts to H0, then we already have that theta 1 prime is a Cartan involution of H0. So this amounts to proving the following. So we only have to see that theta 1 prime sigma prime is equal to sigma prime theta 1 prime. Okay? So let's start by computing theta 1 prime sigma prime. We have theta 1 prime sigma prime by the definition of theta 1 prime is beta minus 1 theta prime beta sigma prime. Now, we also know who theta prime is. This is equal to theta sigma prime beta minus 1 tau prime. And now it goes beta sigma prime. And this is equal to sigma prime beta minus 1 tau prime beta sigma prime. And what I claimed in last session but didn't prove is that beta minus 1 tau prime beta commutes with sigma prime, and thus the sigma prime in the beginning and the sigma prime in the end are going to cancel out. So to check that this is the case, simply note that if we take the relation beta sigma prime beta minus 1 tau prime equal tau prime beta sigma prime beta minus 1, if we now take the conjugate of these expressions, of these two expressions by beta minus 1, so we multiply by beta minus 1 to the left and by beta to the right, we get that sigma prime beta minus 1 tau prime beta is equal to beta minus 1 tau prime beta sigma prime, and beta minus 1 beta, but that cancels out. So the relationship that I used here is simply taking the conjugate with respect to beta minus 1. Okay? And now to finish, since sigma prime commutes with beta minus 1 sigma prime beta, this last expression is equal to beta minus 1 tau prime beta. Okay? So now let's go with the right hand side. We have that sigma prime theta 1 prime is equal to sigma prime beta minus 1 theta prime beta. Now let's write theta prime as let's write theta prime as beta sigma prime beta minus 1 tau prime beta here. Now the beta minus 1 cancels out with the beta, and the sigma prime cancels with the sigma prime. So in the end, what we get is again beta minus 1 tau prime beta. Okay. And now we simply argue as in last session. So we have that theta 1 prime sigma prime is equal to sigma prime theta 1 prime, and this means that theta 1 prime restricts to G0, sorry, to H0, and we also argued that theta extends to theta 1 prime. Okay. This was simply because beta extends the identity, and theta prime already extended theta. Okay. And now theta 1 gives the desired Cartan involution. Okay, so far so good. Okay, so now let's come back to where we left off last week. So the last thing that we did was define real forms of the same kind. So as a brief reminder, recall that we had defined S homomorphisms that were essentially analogs of irreducible representations, and we wanted to see the uniqueness of extensions of certain real forms under S homomorphisms. We already saw that compact real structures extend uniquely under S homomorphisms, and we wanted to strengthen this last result. And the idea was the following. So recall that if we have two involutions of a complex semisimple algebra that were associated to the same real form, then they have to determine the same coset in the quotient of the automorphism group modulo the inner automorphism group. And this was precisely the group of automorphisms of the thinking diagram. And this group is well known. So for example, in the simple case, we have that it has only one element. In most cases, it has two elements when the algebra is SLNC, SO2NC, or E6, and it's the group of permutations of three elements in the case of SO8C, which corresponds to the thinking diagram D4. Okay. So in general, we say that if two involutions or real forms determine the same thinking diagram automorphisms, then they are of the same kind. If if an involution corresponds to an element, if an involution is in the inner automorphism group, so if it determines the identity automorphism, we said that it was of the first kind. And if we only have two automorphisms of the thinking diagram, we say that elements that are not of the first kind are of the second kind. So what we will see is that if we extend a real form to two real forms of the same kind, then these two real forms must be the same extension. Okay? And this comes in the form of the following theorem. So suppose that we have an S homomorphism. And suppose that we are given a real form of G. Okay. So suppose that this real form has two extensions. Suppose that H1 and H2 are real forms of H, such that first, both real forms extend G0, so f of G0 is contained in H1 and f of G0 is contained in H2. And H1 and H2 are of the same kind. Then these two real forms are the same. And the proof of this is very quick from what we already know about extensions under S homomorphisms. So let's consider the real structures associated to all real forms given here. So let sigma, sigma 1, and sigma 2 be the real structures associated with H0, H1, and H2. So then obviously we have that sigma extends to sigma 1 and sigma extends to sigma 2. Okay. So now let's take a compact real structure of G. And let's call it tau. Okay. Then In this case, remember that we can assume that tau commutes with sigma. So let's also assume this. And this will be useful because remember that under S homomorphisms, commuting real structures are going to take the form of commuting real structures under extension. Okay. So if we have that sigma tau is equal to tau sigma, then this determines an involution that corresponds to G0. So we simply call this composition theta. This is an involution corresponding to G0. Okay. And now let's extend everything to H. So let tau prime be the unique compact real structure that extends tau. Now, by uniqueness, we have that sigma prime and tau prime are going to commute. Sorry, sigma 1 and sigma 2 both commute with tau, and they give extensions of theta. So then we have that the involutions, so say theta I, extending theta and corresponding to the HI, are simply theta I equals sigma I tau prime. So if we're able to prove that sigma 1 and sigma 2 are the same, then we also conclude, sorry, that theta 1 and theta 2 are the same, then sigma 1 and sigma 2 are equal, and this finishes the theorem. But now, note that the H1 and H2 are of the same kind, so this means that theta 1 int g and theta 2 int g are the same coset of odd g mod int g. And this means that theta 1, theta 2, recall that theta 1 is its own inverse, must be in the automorphism group of G. Okay. But also, since theta 1 and theta 2 are extensions of theta, we have that theta 1, theta 2 extends theta squared, which is the identity. So the identity of G, which is equal to theta squared, extends to theta 1, theta 2. So we simply combine these two facts, with F being an S homomorphism, and this means that theta 1, theta 2 must be the identity. Or equivalently, theta 1 is equal to theta 2. So from here, we deduce that sigma 1 is equal to sigma 2 by simply canceling out the tau primes in the definition of theta 1 and theta 2. So H1 and H2 are exactly the same real form of H. Okay. So this gives the generalization to the previous theorem that compact real structures are going to extend uniquely under S homomorphisms. Okay. So to finish, I'm going to make a small remark about the relationship between S homomorphisms and another term that was introduced by Dinkin, which is the notion of an S subalgebra. There is also a theorem in the book that explicitly relates these two properties, but since the proof is quite technical and uses a lot of results that haven't been used in the rest of the book, I think we're going to simply skip it. But at any rate, this is the motivation behind S homomorphisms. So Dinkin introduced the following notions. So suppose that we are given a complex semisimple algebra H. So let H be complex semisimple. Okay. And consider a subalgebra F. Then we say that F is a regular subalgebra if it's normalized by a Cartan subalgebra. And now regular subalgebras have, since they are invariant under a Cartan subalgebra by the adjacent representation, we can give a more explicit description of regular subalgebras in terms of the root space decomposition, because note that the complex semisimple algebra H must split as the sum of the Cartan subalgebra T, to say that T is the Cartan subalgebra that normalizes H, plus the sum of the root spaces. Sum of the root spaces, which are all one-dimensional because we're in the complex case. So since F is normalized under T, it's an invariant subspace for the adjoint representation restricted to T. So it's equal to its intersection with the invariant subspaces, which are precisely the root spaces. So what this means is that we can write F as a certain T tilde plus the sum over a certain subset sigma tilde of the H alpha, okay, where T tilde is contained in T and sigma tilde is contained in sigma. Okay, so we're simply taking a subspace of T, which may be 0, and theoretically we're taking subspaces of all the H alphas, but since the H alphas are straight lines, this means that either we take H alpha or we don't take it. So this is going to be the general structure of a regular subalgebra. In fact, Dinkin in reality introduced the term of regular subalgebras in terms of this decomposition, but it's obviously equivalent to being normalized by a Cartan subalgebra. Okay? And an obvious example is, for example, if T is contained in H. So for example, if T is contained in H, so if T is contained in F, then F is a regular subalgebra. Indeed, because simply take the bracket of T with F, and this is contained in the bracket of F with itself. So this is this gives a family of examples of regular subalgebras. So, at any rate, we will say that the subalgebra F is an R subalgebra if it's contained in a regular subalgebra that is not the total of H. It's in a proper regular subalgebra. And we will say that it's an S subalgebra otherwise. And this proposition that again is stated and proved in Onishchik, they will not go through the proof here, relates a homomorphism being an S homomorphism to its image being an S subalgebra. So proposition homomorphism from a complex semisimple algebra G to another H this is an S homomorphism if and only if f of G is an S subalgebra H. Okay, now we have this property of homomorphisms that is described only in terms of subalgebras. And now to finish, I'll simply give an example of an S homomorphism, or equivalently an S subalgebra that is not irreducible. So recall that when we wanted to motivate the notion of S homomorphisms as being generalizations of irreducible representations, we have this following this lemma that said that if we have a representation taking values of a subalgebra of GLB, then if the representation is irreducible, then it's an S homomorphism independently of the subalgebra H that we choose as the codomain. But in the case that G was semisimple and H was either GLB or SLB, we could go backwards. Okay? And what we will see is that this is not true in general. Example. So suppose that V is a complex vector space. And H is a semisimple subalgebra of GLB. So we already know that if we have a subalgebra subalgebra f of H that is also semisimple, and that is irreducible as a representation, then this gives an S subalgebra, or equivalently an S homomorphism. Now, in the case that H was SLV, then the converse already holds. So S homomorphisms are the same as irreducible representations. And one can prove, so Onischik simply states this as a fact that may be proven that this is also true. So we have this equality of S homomorphisms and irreducible representations, the same holds for the following cases. So H to be SOV whenever the dimension of V is odd, or when H is SP of V. Now independently of the dimension of V. But on the other hand, one can prove that if we consider the dimension of V as even, then it's not true that S homomorphisms are the same as irreducible representations. So if this is false, for H equals SOV. And the counterexample is given as follows. So simply write B to be equal to C to the 2 times R plus S plus 1, where R and S are simply positive integers. And now choose this algebra F in SOV as follows. Take it to be F equals SO to R plus 1 C, acting on the first 2 R plus 1 components, plus SO to S plus 1 C, acting on the last 2 S plus 1 components. So to be more precise, this would be the matrices of the form X00, Y, where X is in SO to R plus 1 C, and Y is in SO to S plus 1 C. Okay. And now one can check that this is an S subalgebra of SOV. So, or in other words, the inclusion of F in SOV is an S homomorphism. But obviously, this is not an irreducible representation because it has the first 2 R plus 1 components as an invariant subspace and the last 2 S plus 1 as an invariant subspace. So, but this is not an irreducible representation. So the main takeaway from here is that when we want to say that S homomorphisms are the same as irreducible representations, we always have to make sure that the codomain is the adequate one, because we will usually work with H to be SLV. But if we change H, then it may be the case that these concepts are not exactly the same. Okay, so this is all that I have for the chapter. So I don't know if there's any last questions on the chapter, something like that. So if there are no questions, then we are done with chapter 6. So in the next session, we will start with the 7th chapter of the book.